Thanks to everybody for coming. My name is Bill Davids. I'd like to talk today about some work that I've done with my PhD student Andrew Skank on the development of nonlinear finite element analysis methods for the load rating of concrete girder bridges. A little bit of background. There are a lot of older T-beam bridges out there, 50, 60, 70 years old. They're in good condition and perform well, but they have low flexural rating factors. And the rating factor is just the ratio of capacity to demand. If it's greater than 1, the bridge is good. If it's less than 1, the bridge may need to be strengthened or posted or closed. DOTs are very interested in accurate rating factors, and when we compute them using conventional AASHTO provisions, we often get conservative values. We can increase them essentially in 3 ways. We can do field live load testing, linearly elastic finite element analysis, or nonlinear finite element analysis. As an example of load testing, we assessed 9 older T-beam bridges with low rating factors in 2017 and 2018. And out in the field, non-destructive live load testing, and the results are shown below in the table, where all 9 of those bridges had rating factors less than 1. And through live load testing, we're able to increase the rating factors to a value greater than 1 for 6 of those 9 bridges. Of course, 3 of them still have low rating factors. The objective of this study was to develop a computationally tractable nonlinear finite element modeling strategy for load rating. We didn't pursue non-destructive live load testing further. We had gone down that road. It's time consuming. It can be quite expensive. It's a valuable tool, but it's not trivial to implement. And when we modify rating factors using non-destructive live load testing, it does require the extrapolation of service load response to predict ultimate capacity. That inherently is going to introduce some errors in the process. Similarly, with a linearly elastic finite element model, we can't capture rebar yielding, concrete cracking, load redistribution, and those models also extrapolate service load response to ultimate response. So they suffer a bit in terms of the gain that you can achieve in rating factor. Now, nonlinear proxy finite element analysis was developed to overcome those issues. We could go straight to a solid nonlinear finite element analysis, but our concrete nonlinear constitutive modeling is complex and difficult to implement in 3 dimensions. The solid 3-dimensional finite element model computational time is very significant, and that's why we went down the road of proxy finite element analysis. It overcomes these issues with a coupled simulation where it's shown graphically in the bottom here. We start with the real beam cross-section. We come up with a simplified proxy section that allows us to build a computationally tractable nonlinear finite element model. And the basis for this, the basis for PFEA, is moment curvature analysis of a single girder. This is well established. It allows you to capture bending ductility. It eliminates the need for that complicated 3D nonlinear constitutive model for concrete and explicit modeling of the rebar. And it also allows the use of code-specified age-dependent material properties. And these are well-defined and understood. Practicing engineers can go to the AASHTO manual for bridge evaluation and, given the age of the structure, get a value for F prime C and a value for the rebar yield strength, and then you have what you need to complete the process. And then we can extend that single girder model to a 3D finite element model using straightforward material properties, shell elements, and it becomes very computationally tractable. So in an overview of the PFEA simulation process, it's shown here. It's really a 4-step process where we first determine that moment curvature response of the real reinforced concrete beam section. And then we have to determine the properties of the proxy section using a multi-parameter optimization to match moment curvature response. And that figure in the upper right shows the proxy section. We have 6 parameters. We don't necessarily need to use all of them, but we treat the web as elastic plastic and the slab as elastic, and with the dimensions in there, it gives us 6 parameters. And we can tune those through nonlinear optimization so that the moment curvature behavior of the real girder matches almost exactly that of the proxy section. And that's shown in the figure in the bottom right, where you see the blue line is the behavior of the actual reinforced concrete section, and the red line is showing, well, that's what the proxy section, that's how it behaves. Now you've got a model that you've got a girder cross section that you can easily model in 3 dimensions, tie all the girders together in your multiple girder bridge with shell elements, elastic and elastic plastic materials, relatively straightforward to do. And in step 4, you apply increasing multiples of load, in this case in HL93, using nonlinear analysis and a RIX or arc length solver up until you get failure of a girder, and that defines the capacity of the bridge. From that, you can compute the rating factor in a fairly straightforward fashion. Here's an example of what a 3D finite element model would look like. So after we determine those proxy section properties, we built, in this case, a model of a 5 girder bridge. You can see the ends of the girders sticking out and the diaphragm at the end, the deck on top. Fairly refined mesh. It looks pretty complicated, but in reality, you can turn over a solution for this in less than an hour or so on a fairly modest desktop computer. We've done some experimental validation. I'll get into some a little bit later, but this is just an example of how we can predict load deflection response of a single girder very well with moment curvature analysis. It gives us confidence in this fundamental building block of the technique. The 3 solid lines up there represent test data we gathered on a completely different project 5 or 6 years ago. So this is load deflection response of a girder. And you can see that we built a proxy section model using the properties of the concrete and the steel that we knew from independent testing. And we have the moment curvature response based model that's giving us a very good prediction of what we observed in the lab. A little bit on the conservative side, but there are good reasons for that. And a little conservatism is not a bad thing when you're assessing capacity of the bridge. So after we ran our PFEA for the 9 T-beam bridges we originally looked at, we got some very interesting results. And you can see here in the table that, again, the field testing only increased the rating factor to values above 1 for 6 of the 9 bridges. With PFEA, we got those remaining 3 bridges with rating factors less than 1 to RFs up above 1. And that's that's good. That means that those bridges have sufficient capacity. They don't need to be posted or strengthened or closed. And I want to take a close look at a couple of these, 3356 and 2390, that I've highlighted here in bold and italicized. Those are particularly interesting case studies, and we'll talk about those. So if we look at 3356 first, that bridge was characterized by a very small exterior girder, and the cross-section is shown at the bottom of the page, and you can see it had 5 original girders carrying traffic, and then on the right-hand side, the rightmost girder, it's a smaller girder, it has less reinforcing, it's got a narrower web. It was originally designed to carry a sidewalk, and when they widened the bridge in the late 1970s, it was repurposed to carry traffic load. And the rating factor for that bridge was governed by the strength of that lighter exterior girder. When we field load test it, or we conduct linearly elastic FEA, we capture the response under service loads, they still predict that that girder is going to fail at a very low load. And that's because they're extrapolating that linearly elastic service load response. With PFEA, we simulate that bridge, we capture the true ductility of that exterior girder. As it deforms, it will shed load to the other stronger girders on the interior, and the bridge as a whole has sufficient capacity. And hence the higher rating factor for this bridge. Bridge 2390, that was of particular interest to the Maine DOT. Non-destructive live load testing only increased the rating factor from 0.76 to 0.84. And they actually hired a consultant, AECOM, to do a linearly elastic finite element analysis and base a rating factor on that. And that gave an RF of 0.92. And the Maine DOT Bridge Posting Committee came to us at UMaine and requested input based on our PFEA rating analysis. Could we use that for this bridge? And so I met with them back in early July of this year. And we had actually done our own, independently, our own linearly elastic FEA-based rating factor and got 0.95. So that validated what AECOM had done. We were getting very similar results. I overviewed the PFEA concepts with the Maine DOT, and we discussed it over the course of an hour or so, and they ultimately accepted that that bridge does have sufficient capacity. It's got a rating factor greater than 1. They don't need to post that bridge. And indeed, the main DOT is interested in conducting additional PFEA ratings for some structures because of its relative efficiency and its sound mechanics basis and ability to give a better picture of capacity than a linear analysis. We have done some additional work with PFEA. We've validated with additional experiments conducted by others. We've extended it to allow the rating for shear at the supports, which can also be an issue with these older concrete structures. It's also been extended to allow the load rating of pre-stressed girder bridges. This image shown here is load versus deflection. The blue data with the symbols, that's actually information from a load test of a decommissioned pre-stressed girder bridge that before it was torn down, it was actually loaded to failure in the field. So it was a true, three-dimensional test of a full structure. And the PFEA predictions we developed using only the published information on that bridge. And we predicted what you see here by the red line, and you can see the prediction is very good. Now PFEA does predict more capacity and more ductility than what was observed in the field, but there's a very good reason for that. At a load of about 220 kilonewtons, the shear connectors between the deck and the girders failed, and they lost composite action, and the bridge failed prematurely because of that. And interestingly, you can go to the PFEA analysis results and look at the force in the connectors predicted by PFEA, and indeed, they should have failed. They failed at just about the capacity that AASHTO predicted the connectors had. So I would say that's a really good prediction by PFEA in light of that. Now, I've talked very positively about the method, but there are some shortcomings. I mean, the first thing we have to recognize is the rating factors are based on expected response at capacity. So at capacity, the structure has undergone a lot of inelastic deformation and load is redistributed. Those large rating factors we get don't necessarily imply that we can put big overloads on the bridge without damaging it. We have to keep in mind where's the onset of damage. That may dictate the largest truck that can be put on the bridge. And that's important because DOTs use rating factors to help inform them about whether they can give an overload vehicle a permit to travel on a bridge, for example. PFEA may not be applicable for large girder spacings. We assume the slab is linearly elastic. That was a very good assumption for the bridges we looked at. We verified it's a good assumption, but it could be unconservative if the slab is going to undergo significant inelastic bending deformation. And if you get large girder spacings, that could be the case. The moment curvature analysis and the optimization inherent to PFEA are additional necessary steps. Those are things we have to do. And it does require the use of some powerful commercial software. We're using Abacus, but you need Abacus or ANSYS or something of that nature to conduct those 3D finite element analyses. So with that, I'd like to close and thank everybody for listening, and I'd be happy to take any questions you may have.